Yeah, so we'll start off with question one here. Question one, right? Of the following transitions in the Bohr hydrogen atom, the blank transition results from the emission of the lowest energy photon. So emission means we need to be releasing energy, right? So to release energy, we have to go from a high energy to a lower energy. So immediately we can cancel out A. I can cancel out D. I can cancel out E because those are all absorption. We're going to a higher energy, so we're absorbing energy on the way up. Um, so that leaves choice B and C, right? And so we are looking for the lowest energy photon. So remember, these steps are not the same size, right? So each step represents a step in energy. So in general, right, the more steps you go, the more energy you're absorbing or releasing if you're on the way down. So 6 to 1, right, going down 6 steps is releasing a lot of energy. 6 to 3 would be releasing less energy because we're going down fewer steps. So two things, right? Emission, we're looking for going from a high energy level to a lower energy level. And then the lowest energy photon, we're looking for the smallest number of steps that we're transitioning between, remembering that step one, right, is the highest energy. And then each successive step gets smaller and smaller and smaller in energy. All right, question three, rank these forms of electromagnetic radiation from smallest to largest based on their frequency, right? So the frequency is directly related to energy, right? We know energy equals Planck's constant times my frequency. So if it's easier for you to think about energy instead of thinking about frequency, basically high frequency, high energy. So the highest energy here would be gamma rays, A, because that's the farthest to the left on the electromagnetic spectrum. All right, what would be next is, oh, we want to go from smallest to largest. So just kidding, I'm starting off in the wrong direction. So smallest frequency is going to have smallest energy. Um, so our smallest energy is going to be out there with radio waves, right? So choice E is going to be the smallest energy. After that, we're going to have microwaves and then IR, because IR is just below red light in the visible region. And then after infrared, then we would go through the visible region, red all the way to blue, violet. After visible, we would get to UV. So UV is next. All right, and then last would be our highest energy, right? That would be our gamma rays there, as we're kind of working from right to left across our electromagnetic spectrum. All right, so E, C, B, D, and A for question three. For question four, it's just a calculation, right? We're told that the frequency of these low frequency radio systems that they use in the Navy to communicate between submarines, the frequency 2.14 times 10 to the 4 inverse seconds. We know, right, speed of light equals my frequency times my wavelength, and they want to know the wavelength of this. So we can rearrange this equation to solve for wavelength. Wavelength equals speed of light divided by my frequency. Speed of light, 3 times 10 to the 8th meters per second. Divide that by my frequency. I don't have to do any unit conversion with the frequency because they already give it to us in inverse seconds, right? So that's fine. Divide those two and seconds cancel out. And that's good because we're looking for meters and we're left with meters as our only unit. So we found the wavelength to be, 1.40 times 10 to the 4 meters, right? So a little bit over, actually a couple kilometers. And then I went 3 significant figures because I've got 3 significant figures in the frequency that's given there for question four.
I have a question about question three.
Sure.
Are we just supposed to have that memorized, or is there an easy way to tell which one's higher?
I mean, you don't need to memorize, you don't need to have it memorized, but um, kind of just know like some points in that spectrum. I mean, so like gamma rays and X rays and UV rays should all be pretty easy because they're all things that we're afraid of, and we're afraid of them, and we protect ourselves from them because they're really high energy, right? When you're getting an X ray, there's a reason why you wear a lead vest on anything else that's not getting X-rayed, or why the X-ray tech stands behind a wall while you're doing the X-ray to minimize their exposure. So just kind of know like the high end, right? Gamma rays, X rays, UV, the low end, right? Radio waves, TV waves, low energy. Um, and then you definitely should know the visible region. Like you should know, okay, red light is on the right side of the electromagnetic spectrum, which means red light has a longer wavelength and is lower energy than blue light, right? Blue light is on the left side of the electromagnetic spectrum. So blue light has a shorter wavelength, higher frequency, higher energy. And if it helps, right after the blue light, right, the next band is UV. And again, that's what gives us a sunburn. That's what we try to protect ourselves from because it's higher in energy. Um, so I'm not gonna give you the whole, chart. You don't really need the whole chart. Like you just kind of need to know where a few things are in that electromagnetic spectrum. And then within the visible region, you should just know the ends, right? That low energy, red light, high energy, blue light, um, for the exam. So I think that answers Robert's question and Lindsay's question. And then Annie's question, right? I will give you all those constants, right? And homework seven's, yeah, we could look at homework 7 after the practice exam. All right, question 5. That answered everyone's questions. Right, so for question 5, let's see, I wish this came up on one page, but it's split between pages here. So they tell us wavelengths of the emission spectral lines for a given element are blank, the wavelengths for the absorption lines for the same element. Let's see if I can find my page here. All right, so if we take a look, the wavelengths of the emission spectral lines for a given element are blank, the wavelengths for the absorption lines for the same element, right? And basically what we're going to see is that the energy, right? The energy, as we kind of saw in the Bohr's model of we've got these different energy levels and electrons can move between these energy levels, right? As they move up, they're absorbing that energy. As they move down, they're going to release the same energy that's between those two. So it should be equal to the energy absorbed should be equal to the energy that's released, because again, it's a step. So just like you go up 2 steps in elevation, you go down the same 2 steps in elevation. So the energy would be the same for those electrons as they transition between those 2 steps. All right, there's our first 4.